Welcome to the first technical session of CPAIOR 2021 after the wonderful masterclass we had yesterday. So today is we're starting with the best, the lead off. So the very first paper is the paper winning the Best Student Paper Award. And it is titled Improving the Filtering of Branch-And-Bound MDD Solvers by Xavier, Gillard, Vianney, Coppé, Pierre, Schaus, and Cire. And I guess it will start playing. And you should be able to ask questions in the chat. There should be one of the authors available. Well, I'm looking, I can't see one at the moment, to answer questions right throughout the talk.
Good afternoon, everybody. This is Xavier Gillard from Schaus in Belgium. In today's video, I'm going to tell you about a way to improve the filtering of branch-and-bound MDD solvers. So this talk is going to be structured around 3 parts. In the first one, I will give you just enough background on MDD-based optimization so as to understand the algorithmic improvement that we brought to the framework. In the second part, I will try to explain the intuition of the improvement that we propose. And then finally, I will go over an experimental study that we conducted to assess the performance and the impact of the change we proposed. So dynamic programming, well, MDD-based optimization is basically dynamic programming, the exact same dynamic programming that you've been using when searching for shortest path in a graph with Dijkstra's algorithm. But instead of considering the problem in terms of recursion, it is considered as a label transition system, which is easily compiled into a decision diagram. This is nice and well because an MDD provides you with a compact encoding of the solution space. And as a matter of fact, when assuming maximization, the optimal solution in your MDD is going to simply be the longest path in that MDD. But there's a major flaw that compiling the decision diagram might require a potentially exponential amount of time and memory. This is why we have to work around the memory limitation. And a few years ago, Bergman, Cire, and Vianney have proposed a branch-and-bound framework based on MDD, which effectively works around that limitation. And what they do is that they use bounded with MDDs. These are MDDs which are not exact, which will only provide you with an approximation of the optimal solution, but that have the major advantage of never exploding in memory. So the size of these MDDs, even though these MDDs are inexact, is guaranteed to have maximum bounded memory usage. And they use 2 types of bounded with MDDs. The first one is called the restricted MDD, and it is built as follows. Given that you want to, in this example, for instance, given that you want to have a maximum layer width of 3 nodes per layer, you simply delete the nodes that go over that are heuristically chosen to be the less promising ones. You just delete them, you never explore them, and that means you have a much smaller MDD to explore. And the good thing about this approach is that it does provide you with a lower bound on the optimal solution. The longest path in that MDD, even though the MDD is not exact, is a lower bound on the optimal. The second type of bounded with MDD is called relaxed MDD. And instead of just deleting nodes, this one chooses to merge them. And provided that the relaxation that you use to merge node is correct, the longest path in your MDD is going to be an upper bound on the optimal solution. These 2 approaches are nice and well, but there's a third use for the MDDs in that framework. If you consider the next layer, the first layer, you'll see that there was no merge, nothing, no change, no deletion, no merge, and that the beginning of the MDD is absolutely exact. So we will, this framework proposes to simply use what is called an exact cut set of nodes. That is a set of nodes which are all exact, in which all paths from the root to the node only go through exact nodes, so nodes that haven't been merged or deleted, and to use them as a way to enumerate the subproblem that remain to explore. But we'll come to that a bit later. In a nutshell, what I want you to remember about MDD-based optimization up to this point is that MDD-based optimization is nothing but dynamic programming, with a means to control the memory explosion that you might face when solving the problem. This brings us to the second part of this talk, when I go over the improvement that we propose over the Bergman-Cire baseline. Essentially, we propose two techniques. One which is called rough upper bound, which basically consists of a cheap problem-specific heuristic, cheap problem-specific bounding procedure, which is executed at each node of the MDD to decide whether or not the node must be explored or not. And the second one is called local bound, and that basically consists of attaching a bound which is computed during the compilation of a previous MDD to each node, and this allows us to do some more pruning. But let's first focus on the rough upper bound. Like I told you, it's a very cheap problem-specific procedure to evaluate the upper bound on the given value of a subproblem. And this very cheap procedure is used while compiling a diagram. That means that it's basically the same idea as the branch-and-bound, but during the compilation of the MDD. So let's go over an example. Assuming that we have this root node, we can enumerate its sounds, and for each of the sounds, we're going to run our procedure and see whether or not the bound provided by the rough upper bound is above or less to the best known solution. In the case of this first node, let's assume that the rough upper bound is below that of the best known solution. That means that we know that any subproblem below that first node is never going to bring any improvement. So we just simply decide to not explore the node and move on to the next one. Again, we repeat the procedure, and we see that this time the rough upper bound is above the best known solution, the value of the best known solution. That means that we simply expand the node and generate the successors. We repeat that for the third node, and again, it's above the best known solution. And we do that, as I told you before, we do that for each and every node in each layer, and that means that we are going to compile a much smaller MDD. If you compare that with the MDD from the original MDD, you see that the size of that MDD is much smaller. It is much smaller, but we haven't lost anything. We have the same guarantee as in an exact MDD. That means that we have generated much faster MDD, and also that given that there are much less nodes per layer, chances are high in the case of relaxed MDD that we will have to merge less nodes and have therefore much tighter relaxation per node. The second technique that we propose is called local bound. So if you consider this example, you'll see that the longest path between the root and the sink of that MDD is 102. That means that the lower bound provided by this MDD is 102. But this is not the case for all the nodes in the cassette, for instance. This is not the case of all longest path in this MDD. If you go for the longest path going through the leftmost node, you'll see that it's only 16 and not 102. So the intuition here is that we want to attach that information to each node from the cassette. And we have, like I said, a global upper bound, which is derived from that relaxed MDD, and that global upper bound is going to be 102. That does not change. But we attach an additional information to each node. And that additional information is what we call the local bound. That local bound is basically the length of the longest path going through this node. So for the rightmost node, the longest path is going to be 102. And that is the exact same value as the global upper bound. But for the rightmost node, the local bound is going to be only 16, which means that whenever we're going to pop these nodes from the fringe of the solver, chances are high that the local bound of value 16 is going to be discarded right away because there's a better known solution than 16. And that means that this complete subproblem will be discarded. Okay, these were the two improvements that we proposed over the Bergman-Cire baseline. This brings about the question about MDD-based optimization. Okay, it's nice, you explained nice things, but is that still a thing? Is that still a thing? Does it work? And here's an experimental study that we conducted on 4 problems. We conducted our experiments on the maximum independent set problem, the maximum cut cell problem, max2 set in traveling salesman with time window. And for each of these instances, we generated, for each of these problems, we generated random instances and we solved them with all solvers, and if possible, we tried to solve them with Gurobi as well. So the first thing to observe here is, in the case of MISP, it's that it scales very, very well. The upper line shows that it's the best performing solver when it's given 24 thread to execute. Also, on a single thread, you can see that there's a massive improvement between the baseline version, which is the standard Bergman-Cire framework, without any local or rough upper bound, and the lines above all show that there's improvement, and those lines above are the resolution with our framework. And an interesting thing to note here is that with both rough upper bound and local bound enabled, our solver outperformed Gurobi on one single thread. Just using one single thread, our solver do better than Gurobi when using 24 threads. And that's, we believe, quite an achievement given the performance of Gurobi. For a second problem, we observe kind of the same. In parallel, our model scales very, very well. It's actually the only solver that was able to solve all instances and to solve them quite fast, actually. In about 800 seconds, all instances were solved using the parallel version of the solver. Also, we can observe that the improvement between the baseline version and the enhanced version with rough upper bound and local bounds is quite dramatic. Even though in this case, even our best performing solver is no match for Gurobi, it is quite close when using one single thread. But as I said before, the parallelism does bring quite a lot of improvement in the Branch-And-Bound framework. We repeated the same experiment with the max2 set problem, and we can see that, again, parallelization is quite dramatic. We see massive improvement, and just like in the case of MISP, we see that even the single-threaded versions of our solvers perform better than Gurobi. It's not always clear which of the improvements of either rough upper bound or local bound brings the most, but what is clear is that we observe that on all problems, the version with the combined 2 heuristics improve quite a lot. And finally, on the traveling salesman problem, we can see that, again, parallelism is huge. It provides huge benefits. We also see that, again, there doesn't seem to be much benefit from using the local bound in this case, but we see also that the combined version is once again the one that performs the best. So it doesn't hurt to use it, and that's quite natural actually, because the complexity of computing a local bound is only linear in the size of the MDD, and yeah, that's about it. Again, there's an improvement. It's not as dramatic as compared to the parallel version, but it does bring an improvement. And again, that technique scales very, very well. So that's about it for my talk. I hope you enjoyed it. And if you want to give a try to the code, it's open source, so feel free to give it a try. You can reproduce all of our experiment because all code is online and available for free, so I'll happily answer any question you might have right now.
All right, so let's turn on the microphone at CPAIOR so we can actually have an audience give some applause to Xavier. We should take advantage of the fact that we have a hybrid conference, because actually otherwise the applause is very distressingly non-existent. That's something I always find with online conferences or online meetings. So Xavier's there, ready to answer questions. So if there are any questions, you can just speak up, or you can raise your hand in Zoom. I guess if no one asks now, I can ask Vianney if there's any questions from the audience there. Oh, there is a question from the audience there. So take it away, Vianney.
No, it's already on. And just,
okay.
You don't even have to talk into it.
I can talk like that?
Yes, that's fine. Yeah.
Okay, I have a question. My question is, sorry, this is not exactly about what you did and things like that. This is about a relation you made between MDD and DD and dynamic programming. I'm not sure that this is exact, because usually dynamic programming is based on the Bellman equation and the Bellman optimality principle. And I don't think that this is exactly true here. This is something that we see, that we can read regularly, but what is really your opinion? Because I don't see any Bellman equation or optimality of the Bellman equation that is followed here. So I have some doubt about this relation. What do you think about that? Sorry for that question, which is not exactly on the method you provide, on more on the general introduction.
Wow, that is quite a tough question, actually. Well, I do believe that MDDs are indeed more general than dynamic programming. You can do more with MDDs than just DP. But you can translate dynamic, and you can compile dynamic model into dynamic programming model into an MDD, and that only requires a small shift in the way you envision the dynamic programming model. Instead of having a recurrence equation, you consider it as a labeled transition system with an initial value, initial state, transition relation, transition cost function. And in that case, I mean, it works well, and I believe it's perfectly fine. If you have trouble agreeing on the fact that an MDD is a valid representation of some dynamic programming model, you can check one of the paper from it was Huke, who mentioned all the conditions required for the correctness of the method.
All right. Any questions about? I've got a question about the actual paper. You didn't talk much about the parallelism. So where do you take advantage of parallelism in your MDD solver?
Actually, what I do is I use quite a coarse-grained approach where I pop nodes out of the solver fringe and I just process them in parallel. That means that I develop relaxed and restricted MDDs in parallel. It means one per thread, basically. And it's only when the restricted and relaxed versions of the MDDs have been compiled that I check versus the best known solution, and that I improve and feed the Branch-In.
All right, so it's essentially a kind of portfolio parallelism then. Or is it you're building the nodes in parallel?
Yeah, exactly.
Okay, I'm misinterpreting your last comment. So you're building two MDDs in parallel with multiple workers helping you build.
Yeah, that's exactly what I'm doing.
All right, so we come to the end of our time allotted, but there will be plenty of opportunity to talk to the author in the Discord server after. So please take advantage of that, and let's give him some more applause.